No bummer. Okay, so let's talk about mathematical models. So this section talks about mathematical models, but there's only a little bit I want you to take from it. We're going to talk about linear models a little bit, and then we'll also talk about some models that are quadratic, and then graph some trig functions, because I know trig is your favorite. That was sarcasm in case that wasn't clear. Okay, so how you start with modeling stuff. If you take a statistics class, you're going to do a lot of this, but you've got some real world problem, and you're like, how am I going to deal with this? We'll make it an exclamation mark, not a question. And then you make some kind of mathematical model, which you assume some stuff. To assume that maybe the relationship is linear, in which case you can use a line, or it's parabolic and you can use a parabola. Usually the way that you make that mathematical model is you like to graph some data and make some conclusions. Then you draw some mathematical conclusions. And then you're going to do some predictions. And then you're going to test and see if this makes sense. So one way to test and see if it makes sense is you might say, take your data and use like 2/3 of it to make the model, and then you can test and see if it's right by seeing if it makes sense for some other data points that you have, see how close they are to your actual model. And so some things are linear and some things are not. And there's this really, really, really great book that if you had more time, I'd make you read, and we're going to read some parts of it in this class just for kicks. But it's called How Not to Be Wrong. And it's written by a math professor from, I think it's the University of Wisconsin-Madison. And he is hilarious. He's so funny. So sometimes you assume a relationship is linear. And his example was, the question is why should America become more like Sweden when Sweden is becoming more like America? Okay, so I am partial to Sweden because I lived in Sweden and I speak Swedish. So don't swear at me in Swedish, I'll know what you're saying. But, so he said some people's idea was that, here is the black pit of socialism. Can you see his hilarious already? And here is libertarian utopia. This is just, I'm not talking politics really, but He's like, okay, well, Sweden is going in this direction, so why should we be more like them, right? That's assumption that the relationship is linear, and the libertarian utopia with all freedom is awesome, and there's that black pit of socialism over there in Sweden, and it's just terrible in Sweden, okay? Or he said you could have this assumption that, okay, well, the curve is more like this, and there's kind of this like good point where there's a balance between those two systems in the middle. Does that make sense? And so his point in that book was about that, okay, well, if you assume the assumption that the thing is linear means the picture looks like this versus maybe there's a middle point that's the best, which looks like the right picture. Okay, so that's an idea of what a linearity assumption might look like. And his book is really funny. He's got a chapter of that book there's the one page in which he describes calculus. He teaches you calculus in one page. So we're going to read the one page where he teaches you calculus because it'll give you a good idea of what we're going to do. Okay, but for now we're going to talk about models that are linear. So we have two variables that are linear related, or y is a linear function of x. So in that case, you assume the graph is a line, and it means you can use all the stuff you know about lines to make a formula that models the situation. So what is the most common equation? If I say equation of line, you guys say what? Exactly. That's the part that your Algebra 1 teachers pounded into your skull, right? Now, another really useful way that I will admit I didn't know well when I first started taking calculus is the point slope form. Y minus y1 equals m times x minus x1. You can use this one to get that one. I'm going to admit that I'm going to favor the use of the second one an awful lot. It allows you to take a point and a slope and then get the equation of the line. You can do that with the first one too. The second way is just a lot cleaner. Has anybody ever been told where that second formula comes from? I can tell you, okay? What is the formula for slope? y2 minus y1 over x2 minus x1, right? And the slope is the same no matter what 2 points you pick, right? So what if I wrote that as y minus y1 over x minus x1? And you multiply by x minus x1 and it gives you that equation. So that point slope equation comes from the fact that if you have a specific fixed point and the slope, the other y and x can be any point at any point you want, and the slope will be the same. But it is just rewriting that slope equation in a slightly different way. Does that make sense? So now it's a little bit less magical, but that's where it comes from. Okay. Okay, so here's another example. Recent studies indicate that the average surface temperature of the Earth has been rising steadily. Whether or not why, we're not going to discuss, but it has been going up. Some scientists model the temperature by this linear function. So T is equal to 0.02 T plus 8.5, where capital T is the temperature in degrees Celsius and little t represents years since 1900. So what do the slope and t-intercept represent? That should be a question mark. I can't English. So first of all, what is the slope? 0.02. What is the y-intercept? Okay, great. Now, if you think about slope, the equation for slope is y2 minus y1 over x2 minus x1. You can look at that equation to get a hint at what your units are going to be. Do you see what I mean by that? The slope's units will be y's units over x's units. So in this case, our y is capital T. What are capital T's units? Degrees Celsius per, and then what are the units of the x's? Or in this case, lowercase t's would be, someone said it? Years. So really it's degrees Celsius per year. So what does that 0.02 mean in a semi-complete-ish sentence? Ish, I'm not going to really rate your English because I don't want to. The temperature is doing what?
For each year that passes, the average temperature raises 0.02 degrees Celsius.
And I probably should say, you said it well, you should say the average temperature. What would the slope look like if the temperature were decreasing? It'd be negative, right? Yeah, exactly. Okay. So the y-intercept, that is the value when little t is equal to 0. So what year does little t equal 0 correspond to in this problem? 1900. So in 1900, the average global temp was 8.5 degrees Celsius. Hello, there's handouts up front. So use this equation to predict the average global surface temperature in 2100. So what do we plug in for lowercase t?
200.
Yes, 200. So capital T will equal 0.02 times 200 plus 8.5. Okay, decimal rules get me, but I'm going to try. So do the 2 times 200, what does that make? 400, and the decimal moves over how many spots? 2, okay. Plus 8.5, so that's what, 12.5, is that right? Okay. It probably isn't very realistic to use that model to extrapolate that far. Does that also make sense? that usually you don't want to predict things that are going to happen super far in the future because hopefully systems are subject to change. If the temperature does rise that much, we might be screwed. So, anyhow, especially in Alaska. Okay, great. All right, so now that one I already gave you the equation and asked you to sort of like deal with it. The next one we're going to make an equation. So, generally speaking, driving your car depends on how far you drive. How much it costs you to drive your car depends on how far you drive, right? You drive more, it costs you more. You drive nothing, does it cost you nothing? What do you pay even if you don't drive?
Insurance.
Insurance and maybe a car payment, right, depending on who you are. So, tax, exactly. So in May, it cost this person $380 to drive 480 miles, and in June, it cost them $460 to drive 800. So the first thing is you have to know how to take that sentence and make it into math the way that I'm asking. So it says to express the monthly cost as a function of the miles driven. So if you read this, y equals f of x, that is, y is a function of x, right? Does that make sense? Okay, that's almost the exact same thing as that sentence I have braces around. Express the monthly cost as a function of distance. So monthly cost as a function of distance means monthly cost is your y and distance is your x. Kind of like y is a function of x. And I can't do the analysis with any variables but x and y, so I'm going to use x's and y's and change to c's and d's on the end. Here's a note. WebAssign will count you wrong if you use the wrong variables. So be careful that you give it the variables that it asks for. Does that make sense? Yes?
Is that something that you'll go back and check manually?
You get 5 chances to get it right, so I expect that you're able to fix it within those 5 chances. I've also told you now, so you shouldn't make that mistake. But if you email me and you're like, oh my God, what's wrong? I'm like, oh, you put in the wrong variables. Just be careful about that. So the first step is to write those numbers as ordered pairs. So if cost is your y and distance is your d, what would this 380 and 480 be as an ordered pair? Who's the x? Which one is the distance? 480. Which one is the cost? 380. And the other point is 460. Great. And now you can forget about the words for a little bit. If this equation is linear, you want to find the equation of the line. First thing you do is find the slope. So slope is y2 minus y1 over x2 minus x1. So that's 460 minus 380 over 800 minus 480. So I think that you don't really even need a calculator here. It's 80 over how much? Great. You can cancel a 0 and you get 8 over 32. How does that reduce? A quarter. I picked the numbers out specially for you guys. Okay, so that's the slope. Which means it costs you 25 cents per mile. Does that make sense? Okay, it's your cost per mile. And I'll get the equation of the line. So you got y minus y1 equals mx minus x1. You can use whatever point you want. I'm just going to use the first one. So y minus 380 equals a quarter times x minus 480. And the numbers here really are special. Because what is a quarter of 480? And what's the last thing you do? Add 380. Yep. What's negative 120 plus 380? Same as 380 minus 120, right? 260. And let's just put in the right things. So it was C equals 1/4 d plus 260. So already discussed that the slope is 0.25. This is the cost per mile. Or you could say it's $1 for every 4 miles. It's also the same thing. What is the y-intercept? It's 260. What does that tell you? So cost to go 0 miles, which may be your insurance. Hopefully not your monthly insurance, but if you're a boy and you're a teenager, maybe it is. And your car is really fancy. That's like my 6-month insurance rate. Okay. Are you still writing? Good, okay. Okay, so often you're given data in a table and you're asked to tell like what kind of function best fits this data. That really is statistics, and we're not gonna do that very much in this class. Some pre-calculus classes make you actually fit models to like functions and go with it, but it really is not something we're gonna do a lot. But it's just a good idea to know what these things look like and what their graphs look like to say if they are linear or not. So like, for example, would a linear model make sense to model temperature in Fairbanks, Alaska? No, because the temperature in Fairbanks, Alaska does a sort of oscillatory thing, right? It goes up and down in the season, right? So in that case, a model that was a sine or cosine would make more sense. So it's always like a good idea to be able to just like say, okay, well that picture looks like a line, looks like a sine or cosine function, looks like an exponential. Like you wouldn't use a line to model population growth, right? Population growth goes like kaboom. Or if you're the rabbits in Denali, it does like a little up and down thing where it follows you kill off all of your resources and then you have a population crash, and then you rise again and you crash, you rise again, you crash. And the links follow the rabbits. It's kind of cool. So one thing you might have is a polynomial function. So we'll figure out in this class how to find these simple equations. This is like simple basic particle physics. But so this shouldn't be dropped, it should be thrown, but there's a ball that's thrown from the upper deck of the CN tower, which is apparently really tall, and this height above the ground is given by this equation. The reasons are physics, and we'll discuss them later in this class, but for now that's the equation. We want to know, when does the ball hit the ground? So H stands for height, T stands for time. If the ball hits the ground, what is its height? 0. So you're solving this thing equal to 0. Now, if you see a variable that's squared, your options for solving that equation involve either factoring, completing the square, or the quadratic formula. Do you want to factor this? God, no. Do you want to complete the square? Even worse, no. Do you want to use the quadratic formula? Sure, yes, okay. And there's a great, like, you can get this to Pop Goes the Weasel on YouTube. I will not sing Pop Goes the Weasel right now. So what is the quadratic formula?
Negative b
Uh-huh.
plus or minus the square root of b squared minus 4ac
Mm-hmm.
2a.
Yep. You do have to know that in this class. Like, I know you've been taught this repeatedly because I've been through the system and made people learn it. Algebra 1, Algebra 2, pre-calculus, and now you have to get that in your skull somehow. It's how you solve quadratics when you can't, it's like it always works. My Russian husband calls factoring solving by staring because they just use this and nothing else. And for stuff that has nasty numbers like this, obviously a calculator is your best friend. Like, I'm not going to make you do this kind of stuff by hand because that'd be stupid. But let's just plug the numbers in. You get 0.96 plus or minus, negative 0.96 plus or minus 0.96 squared minus 4 times negative 4.9 times 449.36 all over negative 4.9 times 2. not gonna bore you with the details, I'm just gonna tell you what you get. So you get, how many answers are you gonna get, actually, by the way? You're gonna get 2, because of that plus minus. One of them is negative 9.479, and one of them is 9.675. One of those numbers makes no sense in this context. Which one? The negative one, okay? So it is this many seconds after being thrown, that ball will hit some poor Joe Schmo who's on the ground. Okay. All right. If I gave you one of those to work out like on a quiz or something, it's going to have like nicer numbers. It'll be ones you can evaluate nicely. Okay, we also have functions that are rational. So rational functions specifically are ratios of 2 polynomials. And polynomials are functions that only have positive whole number powers, like squared, third, fifth, seventh. No powers of 1/2. Okay, no powers that are negative, just powers that are whole numbers. And the domain consists of all values where the denominator thing is not equal to 0. Nothing really new there. So, find the domain of this function. So which part of this function is going to cause a problem? The denominator, which is x to the 4th minus 1. So you got to figure out where does that equal 0, and we're going to leave those numbers out. So now what's the difference of squares? How does x to the 4th minus 1 factor? X squared plus 1, x squared minus 1. Have you guys seen that pattern before? Okay. Now, technically, this x squared plus 1 part doesn't factor anymore. That's actually prime, so it's done. How does the x squared minus 1 factor? X plus 1, x minus 1. Great. And then you solve each factor equal to 0. X squared plus 1 equals 0, x plus 1 equals 0. You can do this in your head if you're faster than I am. I'm just not going to do it fast yet. So the last two are easy. One number you leave out as -1. One number we leave out as +1. If you were asked to solve this x squared plus 1 equals 0, you get x squared equals -1. So technically x equals plus or minus I. Is I a real number? No, so we don't really care about those. That first factor doesn't give us any numbers to leave out. So the only two numbers we leave out, x cannot be plus or minus 1. And I should have asked for it in an interval. If I hadn't said so, you could lawyer me and say, well, you didn't ask. It's okay, I'll take it. But what is it as an interval? So -∞, what's the first number you leave out? Parenthesis, -1 to 1, and then 1 to infinity. I realize that that's like a gazillion more characters than x cannot equal plus or minus 1. Like, it's annoying, but you do have to know how to do it. Okay. Did you guys learn how to graph sine and cosine? Do you remember how to graph sine and cosine? Ish, okay. I'll tell you where it comes from. Have you heard of the unit circle? We're going to specifically review the unit circle tomorrow, so that we will have a day of this, but here's the general idea. The unit circle is a circle of radius 1, right? That's what the word unit means. So you got a circle, its radius is 1. So this is the point 1, 0. This is the point 0, 1. This is the point -1, 0, and this is the point 0, -1. I didn't dyslexic any of those, did I? Because it's really easy to do that. And on that unit circle, the x-coordinate is cosine of an angle, so given some kind of angle theta. the y-coordinate is sine of that angle. Using the unit circle is how you generalize this idea of right triangle trigonometry, where sine was so opposite over hypotenuse, to things where you no longer have right triangles. Because once your angle inside there gets too big, you don't have a right triangle anymore. Does that make sense? Okay. So to graph the sine function, what you can do is say, okay, I got my unit circle. Sine is all of the y's. So on this axis is theta, that's the angle. We can call it the x-axis too. There's the y-axis. So you start here. Okay, so when your angle is 0, sine is the y-coordinate on that circle. So what is the y-coordinate at that beginning point? 0. So you start at 0. This angle up here is, I can't speak, 90 degrees, or what is it in radians? Pi halves. So at pi halves, by pi halves, what has the sine's value changed to? 1. And if your axes are not labeled by 1s, please tell me that. If you don't label them, I'm assuming they're by 1s. Does that make sense? If they're not by 1s, label them. So by pi halves, you climb to 1. What's happened by pi? 0 again. How about 3 pi halves? -1. And by 2 pi, you're back at 0. Do you see how there are sort of 5 distinctive points there? What's going to happen when you go around that circle again? That pattern's going to repeat. Does that make sense? So that's the basic pattern of one oscillation or one period of a sine function, and that thing's going to keep going on both sides. It is curvy and not straight. They're not V's. They're not lines. The specifics as to why that's true is determined by the values on the rest of the circle, which you'd have to round because they're not nice whole numbers. So, but that's the basic picture. The important thing is to know that sine begins at 0. So to graph that picture of sine, we took all of the y values. How are we going to graph cosine? I'm just going to do it below it, even though it's on my next slide. What values you take for cosine? All the x values. Okay. Okay, so when you plug in 0, what is the x value? 1. So cosine starts at 1. Okay, by pi halves, what happened to your cosine? 0. And by pi, where'd it go? -1, and by 3 pi halves, we're at 0. By 2 pi, we're at 1. Notice that there were also 5 points there. And the pattern would also continue. So that would go down, that would go down. Do you see that they're horizontal transformations of each other? You took the purple picture and just kind of shifted it over. You get the black picture? Yep, exactly. And depending on your perspective, the point is they're definitely the same shape. It's just that where they begin is different. Does that make sense? Okay. So the important thing to really know about those graphs is that there are 5 points that determine what a cycle looks like, and where the cycles begin and end for sine and cosine are a bit different. Okay. We will definitely discuss the unit circle more, because you really have to know it and make you. Okay, did that. Okay, find the domain of these functions. So we got 1 plus 2 cosine x. So you're going to exclude a whole lot of numbers here. So figure out where 1 plus 2 cosine x equals 0, and all the things that make that happen must be left out. Does that make sense? It's the same thing as saying, where does cosine of x equal -1/2? Okay. So there's a circle. in which quadrants is the cosine negative? 2 and 3, great. Because cosine is the x coordinate, right? All right. And then in those quadrants, usually you have this angle, they're divided into 3s, right? Okay. The middle ones are the quarters. So that's an angle of 3 pi quarters. And this one down here is 5 pi quarters. In the unit circle, the easiest points are the points that are on the axes. Do you see what I mean by that? Like this point out here is 1, 0, right? That's the easiest point. The next easiest points are the quarters. We're going to talk about where they come from next time. But at this point, the coordinates are negative root 2 over 2, positive root 2 over 2. So the cosine is negative root 2 over 2. The sine is positive root 2 over 2. Does anybody know what the numbers are at this first one? Negative 1/2 and and this next one they are, yep, exactly, just flip-flop. So assuming you could look at a unit circle and figure this out, at which of those points that I just drew, at which angle, and also what is this angle? So this is 2 pi thirds, and this one is 5 pi sixths. So, and I guess I probably didn't state this, but unless otherwise said in math classes, you always give radians. Like we never use degrees. So there's a reason for that, and I can't remember what it is right now, but I think it has to do with the technical definition of the functions.
Just to make it look scary.
And yeah, it's kind of scary, but big numbers are also scary and annoying because like multiplying huge numbers sucks. These are smaller. All right, so which angle is the problem? 2 pi over 3, because that's the one where the x coordinate is negative 1/2. Okay, so x can't equal 2 pi over 3. And how would you account for the fact that you could go around the unit circle more than once? Plus 2 pi, and you're going to say, I think that WebAssign uses k or n, I can't remember, but it doesn't really matter, where k is an integer. Do you guys know what integers are?
Is it the funny symbols?
Yeah, the funny symbol for integer is z. And the reason it's a z is because a lot of math was done in German, and the word for integers in German begins with a z. I don't care if you just tell me it's an integer, okay? But the integer thing means that you plug in things like 1, 2, 3, 4, 5, 0, or negative 1, 2, 3, 4, 5. They're the numbers that are counting numbers plus the negatives. That's what an integer is. Okay. Does it make sense that this angle down here is also going to be a problem? Because how far over it is the same. That point would have coordinates negative 1/2, negative root 3 over 2. Because it falls in quadrant 3, both the x and y are negative. So what angle is that? So this is 5, 6, 7, 6. I think that's 4 pi thirds plus 2 pi k. Just make sure you use whatever letter WebAssign asks you to use if you get asked a question like this. Like they may say use n for an integer, they may say use k, just use whatever they ask you to use, and so you'll be fine.
The 2 pi means that we're just looking at one circle?
2 pi means that you can, another point that's also problematic is that this number plus going around the circle one more time. Does that make sense?
Okay,
That's what the whole plus 2 pi k means. It means, okay, this number plus going around once, plus twice, plus 3 times. So this lets you get all of the infinite possibilities in one compact form. Does that make sense?
it's just cleaning it up.
Exactly. I want you to give like an infinite list, which would mean you gotta, write an infinite number of numbers. So that's how you represent them. And in this case, I will never ask you for interval notation because it's going to be disgusting. So I'll just tell me what x cannot be. X cannot be those things. Great. I'm going to change my mind and make this one a little bit easier because we're going to graph tangent specifically next time. I'm going to do something we've already graphed. So let's make it square root of sine. That's going to record. Awesome. We're looking for where sine of x is bigger than or equal to 0, right? And that's not an inequality you can just like solve easily, is it? No. So our sine picture looked like this. Right? You can get a second to draw and tell me if you agree. And it would continue, right? Like, so I would, here the next point would be 3 pi, and I would do this thing again, right? Okay. Now, being positive means that graph is above the x-axis or below the x-axis. So you're looking for where it's positive. So you're looking for where the graph is above the x-axis. So from 0 to pi is good, right? How about from pi to 2 pi? Bad. No. From 2 pi to 3 pi is good, right? Past that, no good. If you were to take a calculator and graph root sine x, you're going to get this thing that has these little sort of like circular shapes, but there are gaps between them. So the way to say this domain is to kind of use an infinite interval with a little bit of like dot, dot, dots to say, I know this pattern continues. So 0 to pi is okay. So we're going to go 0 to pi. Do I include those endpoints? Can you square root 0? Yes, so you do include those endpoints. What's the next interval on the right you do? 2 pi to 3 pi. Okay, and then you leave out 3 pi to 4 pi. Who would come next?
Could you use that notation thing? Is there a way to do that?
Probably, but I think it's messy. I'm just going to do this, and I'm just going to say dot, dot, dot. Convince me you know that there's a pattern. Does that make sense?
Yeah.
And then we're good. And just give me 1, -1. So if we graphed in this direction, you leave off from 0 to negative pi, right? What would be the numbers that you would include? Would be 0 to negative pi, the next one would be negative pi to negative 2 pi. And if I'm going to give you those kinds of questions on a test or quiz, I've got to be pretty specific about how I want the answer, because I don't want to take off points because I'm being unfair and picky. But it probably will be the case that I'll ask for like a couple of the subintervals specifically listed. Does that make sense? I don't think there's a great, I can't think of another way to list it using that notation, because it isn't like we're just leaving out specific numbers, we're leaving out whole chunks. Does that make sense? It's a little bit different. It probably is, but I can't come up with it on the spot. Okay. So that's the end of that lesson, right? Short and sweet.